Now what we're going to do is we're going to look at dimensionless parameters. So dimensionless performance is interesting because this is where we start to get into the entire idea of, as I mentioned before, if we have a little airplane, we stick it in the wind tunnel. This is the process that we use to go, okay, I know exactly how that bigger airplane is going to work based on what happens in the tunnel here. So there's a couple things about using dimensionless performance, scaled analysis, scalar analysis, there's a lot of names for it. And it's all based around using dimensionless parameters, then being able to use those to apply it to a different size object. Now the first thing that you have to know is you have to know that the objects are what is termed geometrically similar. To have a geometrically similar item, all of the dimensions of the object have to be scaled by the exact same amount. So if you were playing on the computer and you had a 3D model and you could scale everything 10%, everything's going to scale by 10%. And it's really important that this idea of geometric similarity is held, because if you don't hold these, the things kind of go a little bit wonky. And so this is really, being able to use dimensionless performance analysis is pretty cool, because one of the things you have to remember is a pump is geometrically similar to itself. And you're probably sitting there going, well, why would I care if a pump's geometrically similar to itself? Well, what if you had a pump and you know what everything happens when you run it at 1500 RPM, but for some reason you're only going to run it at 1000 RPM? What happens? Well, your head's going to go down, your flow rate's going to go down, your power consumption is going to go down. So you can use this idea to take a pump and kind of bring it off the pump curve. Or, you know, you've calculated out everything for a system and you're like, okay, I want to use this pump, but the flow rate that I'm going to use it at is, I can't really figure out what the numbers are saying on the curve, but I know what they are at the design point. Well, then you can use this dimensionless performance and go, okay, well, the curve says it runs at 1500. I need a little bit more flow rate out of it to keep that efficiency. Well, let's run it at 1750 and see what happens. That's where this all comes into play. So let's take a look at our performance. And it's going to be based around a couple of dimensionless coefficients. And so the first one that we're going to look at is we're going to look at the capacity coefficient. And so the capacity coefficient is really just what it says. It's a coefficient talking about the flow rate. And so that's going to be C sub Q. That's our capacity coefficient. It's going to be Qn divided by the impeller diameter to the third. Now, you have to remember something here, that this is a dimensionless parameter. So these are all going to have to, everything's going to have to cancel out. So you're not going to be able to run this in gallons per minute, because that's not going to cancel out. You've got that d to the third on the bottom. You're going to have to convert that that flow rate into cubic feet per second. You're going to have to calculate out that diameter into feet so that it all cancels out. And that leaves us with the impeller diameter, because everybody's going to want to use RPMs. Well, you need to convert that over, so it's going to be in seconds. But not only that, because if you're using RPMs are revolution per minute. That's 360 degrees. You're going to have to convert that guy into radians per second. Radians are always an interesting unit, because when you're canceling things out, radians are kind of unitless, and everybody just forgets about them. So if you put this into cubic feet per second, the per seconds will cancel out. You put that into cubic feet, the cubic feet will cancel out. All that's going to be left is radians, and radians are unitless. You kind of forget about them. And then we have our head coefficient. So our head coefficient is talking about the amount of head the pump is going to give us. So that's C sub H. Gravity times the amount of head that we supplied, divided by impeller speed squared and diameter squared. And the last one's our power coefficient. And this is just talking about how much power our pump draws. And so our coefficient of power is going to be the brake horsepower divided by the density of the fluid that we're using, and cubed d to the fifth. Now this is another one where a pump is similar to itself makes a lot of sense for you to be able to do some kind of analysis on, because if you have a pump, and most pump curves are tagged to water, let's say you wanted to move maple syrup, which is quite a bit thicker than water. Well, how do you calculate out how that pump's going to work in that new environment? Well, that's where you change the density of this, and then you match it back to what the water should be. So as we look at this, the efficiency of a pump is going to be what you put into the pump under what you get out of the pump. So what do you put into the pump? Well, you put in power. What do you get out of the pump? Well, I get flow and head out of the pump. And so if I look at those and multiply the coefficient of head by the coefficient of flow rate, I'm left with rho g q h, and then I have it divided by the brake horsepower, and I divide through by all that stuff. What do I end up getting? Well, I'm going to get brake horsepower. So as you plug in those terms into the equation, you're going to end up getting what our definition of efficiency is. So in turbines would just be the reverse, because turbines will use all these same coefficients. We'll have a capacity, a head, and a power coefficient. But things in the turbine are a little bit different, because what do you put into the turbine? Well, I put flow rate and head into the turbine. What do I get out of the turbine? I get out power. And so once again, if you calculate all those coefficients and make those divisions, you get the same thing that we would have gotten with our normal thing. So as we're looking at these, our capacity of head, flow rate, and power, these are typically calculated at the best efficiency point. And then we use them to match up to other pumps to calculate things out. So we will do that in a couple examples from now. We're actually going to use these to say, okay, I'm going to take the coefficient of head from one pump, compare it to the other one to find out what's going on. But the first thing that you need to do is just calculate these out. Once you're able to calculate them out, then we'll be able to use them for a comparison level, and then we'll go from there.